Kinetic and potential energy. The three objectives are going to be to identify and calculate the different forms of energy, use the Work-Kinetic Energy Theorem to solve problems, and to classify and solve problems with different types of potential energy. Let's begin first with our definition of kinetic energy. Kinetic energy is the energy of an object that is due to the object's motion. So this is an object that is moving, just like the kinetic coefficient of friction had to do with objects that were moving past one another, or surfaces that were sliding past one another. We can see here that the kinetic energy is a function of the object's mass and the object's velocity, and the units here are going to be joules. So if you have more mass, you have more kinetic energy. If you have more velocity, you have more kinetic energy. The units again are joules. Let's show that that works. The units of mass are kilogram. The units of velocity are meters per second. That quantity is squared, giving us kilogram meters per second squared times meters. And notice what I'm doing. It becomes meters squared, so I put the meters separately, and the second squared I leave in the denominator. Well, this quantity right here is actually a Newton. Kilogram meters per second squared is a Newton. So this is really a Newton times a meter, and a Newton times a meter from our work formula is indeed joules. So the energy here is measured in joules. Example 1 says a 12 kilogram bowling ball moves at 3 meters per second. How fast must a 4.5 gram bouncy ball travel for it to have the same kinetic energy as the bowling ball? So we want the kinetic energy of object 1 equal to the kinetic energy of object 2. Well, object 1, we know the mass is 12 kilograms, and we know that the velocity of object 1 is 3 meters per second. Object 2, we have a mass of 4.5 grams, which is really 0.0045 kilograms. We do not know what the velocity of the bouncy ball needs to be. That's the question at hand. Now, there are two ways to solve this. First, you could find the kinetic energy of this object just by using the mass and velocity and set that equal to the kinetic energy of the second object to solve, or we can just use our formula right here. So since the kinetic energies are equal, we could say that the energy of object 1 equals the energy of object 2. Now, there's a 1/2 on both sides. Cancel the 1/2s. Those drop off, leaving behind m1 v1 squared equals m2 v2 squared. Again, this only comes about from this one particular scenario. Now we want to solve for the velocity of the unknown, which is the bouncy ball, which is v2. So let's divide by m2 on both sides. Canceling those, we're left with just v2 squared. How do we get rid of the squared? We take the square root. So in the end, we're left with just simply v2 right here. Everything else is gone, and this is our solution for v2. Let's go ahead and plug in our numbers. The mass of the first object was 12 kilograms, so we'll plug in our 12 kg. The velocity was 3 meters per second, so we have 3 meters per second, but that quantity is squared all over the mass of the first object, which is 0.0045. And that's under a square root. Now, before we come up with an answer, let's make sense of this. If a bowling ball has a velocity of 3 meters per second, and then we have a little small bouncy ball, it's got to be going a lot faster than 3 meters per second to have the same amount of energy as a bowling ball. So our velocity was 3 meters per second for the bowling ball, but we're going to notice that our velocity for our answer is much greater than 3 meters per second, because a bouncy ball has to move a lot faster to have the same amount of energy as a larger bowling ball. So we end up with a number of around 155. It's 154.9 meters per second. So clearly we can see here, for small objects to have a lot of energy, you have to have a lot of velocity. So the Work-Kinetic Energy Theorem. Let's take a look at the derivation. Since the work done on an object has to cause a change in its motion, we could try to find a relationship between the work done and the velocity of the object. So we'll start with our definition of work in one dimension. Okay, work in one dimension. So imagine an object here at rest. Suddenly you apply a force to it, which causes it to move. So it's got motion now, but we're looking only at one-dimensional motion. So first, we know that our equation for work is FD cosine theta. But in this problem, since the direction of motion and the force are in the same direction, the angle theta is simply 0 degrees. Okay, again, because it's moving to the right and it's being pulled to the right, the angle theta is 0 degrees. And the cosine of 0 happens to be 1. So this is just 1. So let's really use work equals FD. Now, remember though that the force, or the net force on an object, overall force is always mass times acceleration. F equals ma from Newton's laws. So let's replace F with ma. So the work is really equal to ma times d. But what we can do here is actually write it this way. Let's write it as m times the quantity ad. So we have work is equal to this quantity right here. Now, if we take a minute and take a look back at our kinematic formulas, and I'll leave a little blank here, because we'll fill in above that line in a minute, we could take a look at our formula that related final velocity, initial velocity, our acceleration, and our displacement. Since the object is only moving to the right, instead of x here, we could put d. Again, we could put d there because distance and displacement are the same when an object only moves in one direction. Now, notice, in the original equation up here, we have AD. There's also AD right there. So let's solve for this AD and plug it in up there and see what we get as a result. So let's solve this for AD. We're going to have VF squared minus VI squared all over 2. And that's what AD is equal to. Again, we move the VI squared over by subtracting, and then we divide by 2. So let's take this quantity right here now, VF squared minus VI squared all over 2, and plug it in for AD and write what we get here. So we end up getting work equals still m, but instead of AD, we're going to have VF squared minus VI squared all over 2. And in reality, this is actually m times VF squared over 2 minus m times VI squared over 2. Well, that's actually the kinetic energy formulas. Remember, kinetic energy formulas are 1/2 mv squared. So this is the same thing as this. If we have a change in our kinetic energies, we can simply write this as follows. Okay, remembering that this is really kinetic energy final minus kinetic energy initial. Example 2 says, on a wooden floor, you decide to slide around when you've just put on a new pair of socks. We all know that feeling. New socks can slide around on a nice wood floor. Your mass is 50 kilograms, and you run and start to slide with an initial speed of 1.5 meters per second. So you're running, and then you start sliding. That's the beginning of our problem. You start sliding with an initial speed when you're sliding of 1.5 meters per second. How far will you move if the coefficient of kinetic friction between your socks and the floor is 0.25? So let's list what we know about this problem. We know that we're going to start sliding with a velocity of 1.5 meters per second. But we're going to come to rest. How far will you move? Meaning it's going to stop eventually. So the final velocity is 0. We know that the mass of the object, or the person, is 50 kilograms, and that the coefficient of kinetic friction is 0.25. We are trying to find how far the person will slide. Now, you have to remember what's stopping you from sliding or what's slowing you down. That's friction. So once you are set in motion, friction is the thing that will slow down your motion as you slide across the wooden floor, which is why we're given our coefficient of kinetic friction. So if we think about our work-kinetic energy theorem, we know that a certain amount of work is done on the object due to friction, and we know that there's a change in kinetic energy because we have a VI and a VF. So let's write down our work-kinetic energy theorem. But notice that KE final has got to be 0 because there's no velocity at the end. So work turns out to be equal to negative KEI, the initial kinetic energy. Well, the formula for work is FD cosine theta. Formula for kinetic energy is 1/2 mv squared. Remember the negative symbol that we carried down because it was minus KEI. Now, let's continue. In this problem, we seem to know everything so far except for the force. Well, what force is acting on you or acting on the person to slow them down? That's the force of friction. So let's put a little F there for force of friction. Let's remember that F is really mu Fn. I put mu K because it's kinetic friction because we're moving there. Next, if we think about this and we try to figure out, well, now we need Fn. Think about your free body diagram. Fn acts up, Fg acts down. The person is traveling horizontally only. There's no vertical motion, and there are no vertical outside forces. So Fn and Fg must be in equilibrium. So we could either say Fn minus Fg equals 0, using second law of Newton, F equals ma, or we can go ahead and just say, well, if they're in equilibrium, they're equal and opposite each other. So Fn must be equal to Fg for this to be in equilibrium. So we can replace this Fn right here with Fg. But please remember that Fg is defined as mass times gravity. So I'm just going to put mass times gravity right here. Now what you're going to notice is the following. We don't have theta. We've got everything else. We've got mu, we've got m, we've got g, we've got vi, but we don't have theta. So let's go back and take a look at our free body diagram to figure out what theta was. Well, the object is moving to the right, friction is pushing back. Okay. Remember that the object's motion is to the right, so what we end up getting is an angle here of 180. And we've talked about this before already. Friction does work on an object in a negative way. So we're going to always use 180 for cosine of theta, or for theta, and therefore, if you remember, cosine of 180 happens to be negative 1. So let's just write down what theta is on the side so we remember. So let's go ahead and solve for d, which to me just means divide by everything that's not d. So we can leave our 1/2 mvi squared, but we'll divide by mu k m g cosine theta. Notice mass, mass, cancel. So in reality, we did not need the mass in this problem. So the distance the person slides across the floor is independent of the person's mass. Now we can plug in everything that we know. Let's go ahead and do that. We know the following. We've got a negative 1/2. Initial velocity was 1.5 meters per second. That quantity is squared. That's a 1.5. Mu k was 0.25. G is 9.81 meters per second squared. And we have cosine of 180 degrees. Now, please remember that cosine of 180 is negative 1. So I could just make this a positive and get rid of this completely, because the two negatives end up canceling. So I can, in the end, just look at the quantity that's left, and this will give us a distance of 0.46 meters. So after traveling and running with a velocity of 1.5 meters every second, if you stop and glide on a floor with a coefficient of friction of 0.25, you end up traveling a full distance of 0.46 meters. This is reasonable if you think about the numbers. If you're running, you're taking a step of about 1.5 meters every second, so you're running at a pretty big pace, and you start sliding, 0.46 meters, like 1.5 feet or so. And therefore, you'd slide about 1.5 feet before you came to rest. Let's take a look at potential energy now. Potential. The word potential means having the ability to do something. So potential energy is the energy associated with an object because of its position, its shape, or its condition. Please remember, potential will determine what it actually means. Now, gravitational potential energy has to do with the position of an object, and it's caused by the gravitational fields of interacting bodies. So if we move up a certain height, we gain potential energy, but gravitational potential energy. The formula that we're going to use for potential energy is mgy. M is the mass, g is the gravitational constant on Earth, and then we have to determine what y actually is. Remember from kinematics that y was our change in height, and we're going to notice again it's the same thing. So for example, if the person started at location C, we'll call that ground level. We'll say that this is level 5 meters, and this is a level of 10 meters. If a person jumps from here or somehow climbs the building from here up to here, they gain 5 meters in height. So you'd plug in a 5 for y in the formula. Same thing occurs, though, if you would do this. If you started here and you consider this ground level and you move from 5 meters to 10 meters, then that's also a change in height of 5 meters. So what we're looking for in y is the change in height of the object So example 3 says a 40-kilogram object is raised from the bottom of a well using a pulley system. The depth of the well is 25 meters, and the object is raised 3 meters above the rim of the well. Determine the change in potential energy of the object. So it doesn't matter where the ground is again here. So let's say this is our well. Even if the ground is right here, so the well is sticking out, and then the well goes down another, certain distance. So let's draw the well going down into the ground. Okay? We know that the depth of the well is 25 meters. And then the object is raised another 3 meters above the rim of the well. So again, ground level may indeed be right here and here, but that has no effect on the problem. We'll consider this to be ground level. Okay, we'll consider this to be our ground level, or relative point we will move from. If this is ground level, then we move up 25 meters and another 3, which is a total of 28 meters. If that's our y value, we also need our mass. The mass of this object is 40 kilograms. And now we have the y and the m. We can plug right into our formula. Potential energy of gravity equals mgy. So we have 40 kilograms times 9.81 meters per second squared times 28 meters. Notice the amount of energy that will be involved in this problem will be positive, because the change in potential energy goes from no energy up to some level. We're moving vertically. So y happened to be positive, and therefore our change in potential energy is also positive. You'll get a value of potential energy in this problem of 10,987 joules approximately. Example 4. An ant's potential energy keeps changing since it's constantly walking up and down hills and carrying heavy pieces of food that vary its overall mass. At instant A, it's carrying 3.5 times its mass in addition to its normal mass, and it is at half the height of that of instant B, where it's not carrying food. At which instant does the ant have more potential energy, and by what factor? So let's start with a little diagram. Again, we're saying at A, it's at half the height of B. So let's say this ant is going up these little hills maybe. So let's say that this is the height at A, and this is the height at B. So here's point B, and here's location A. So the ant at location A is there with some food on his back. So here's the ant with a big chunk of food. I use a red circle for the food. And at B, though, the ant is just by itself. Now, we can pick numbers, and that's fine. You could literally just pick numbers. So you could call A, you can call this like 5 meters. And for B, we can call this 10 meters. But really, it makes more sense just to use variables, because we don't have numbers. So what I'm going to do is the following, and this will make sense once you see it. I'm going to call this y, so this would be half of y. Okay, same thing as having 5 and 10 there. And for the mass, well, it's not carrying any food at instant B, it's by itself, so the mass is just m. Not meters, but m for mass. But the mass at instant A is the actual ant plus the food, which happens to be 3.5 times the mass of the ant. So again, we have to use our context clues up here. It says it's carrying 3.5 times its mass in addition to its normal mass. Okay? 3.5 times its mass in addition to its normal mass. Now, in these two spots, we know that the gravitational constant is the same, g, so that doesn't affect the problem at all. So now we have all that we need to know. So let's find the potential energy at point A. Well, at point A, we've got a mass of m plus 3.5 m. So that's just 4.5 m. That's the mass, times the gravitational constant, times whatever the y value is, which is half of y. But the potential energy at instant B is the normal mass m, because there's no food anymore. Gravity is g, and the height happens to be y. So at B, it's just mgy. So that's just a normal mass times gravity times the height, whatever that is. But at A, we need to take a look back up here now and say, well, what we can do is we can bring out this 4.5 times 1/2 out front, and then just put mgy at the end. Because remember that multiplication is both associative and commutative, so we could rearrange the order of parentheses and the order of the variables when they're being multiplied. So this turns out to be 2.25 mgy. So where is there more potential energy? At A, which we just calculated right there, or at B, which happens to just be mgy? Well, just take a quick look. If the energy from mgy was, say, 20 joules, let's say this quantity was 20 joules. At A, we have 20 joules times 2.25. So this is clearly bigger. So our answer for this problem of which has a higher potential energy is at A, even though it's at a lower height. Because remember, the mass is much greater at A. So the mass counteracts this low height. Now the question becomes, by what factor is it larger? Well, the factor happens to be right in front. And the way you find a factor of increase is by taking the larger quantity and dividing it by the smaller quantity. For example, if somebody had $10 and another person had $30, we would say that this person has 3 times as much as this person over here, because we have to multiply by 3 to get there. So technically we could take 30 and divide it by 10 to see the factor of increase is 3. So take this quantity right here, the larger one, and divide it by the smaller one. Well, it's pretty obvious what happens. You're going to end up getting some cancellation. And clearly mgy is going to cancel up top and in the bottom, leaving a factor of increase of 2.25. The next type of energy we're going to look at is another type of potential energy, but it happens to not be gravitational. The height does not matter for this kind of energy. What matters here is a compression or stretch of a spring. So this, again, is the energy stored in an object due to its state of being stretched or compressed. We traditionally use springs to model things. So anything that's vibrating back and forth can be modeled as a spring. A rubber band, when you pull on it, is like stretching a spring, really. It wants to go back to its original shape. So you can model other things as springs as well. What we want to do here is talk about our formula. Now, potential energy in a spring equals 1/2 kx squared. Let's talk about what these are. And our units are still joules because it's energy. K happens to be the spring constant. The spring constant. It could also be called the spring stiffness, the spring rigidity, the spring strength, but K is what's called the spring constant. It measures, it's a property that is specific to each spring, and it measures the strength of force needed to stretch the spring. For example, if a K value is very high, it means it takes a lot of force to stretch or compress that spring. So that would be like a spring that was on the shock system of your car, those big heavy-duty springs. It takes a lot of force to move those. But the spring inside of your ballpoint pen is a small, minuscule spring, not just size, but in strength as well. So that would be a very low K value. Now, K is measured in newtons per meter, and let's discuss why. What this means is the following. If the K value, for example, let's say it were 10 newtons per meter, it would mean that it takes 10 newtons of force to stretch or compress by 1 meter. So to stretch or compress the spring, it would take 10 newtons of force to go 1 meter. That's what the constant actually means here, of 10 newtons per meter. Now, to see what X actually refers to in this problem, let's take a quick look at a diagram, because X, it's a type of displacement, but it's a little bit different from your normal displacement terms. So let's look at a diagram to see this. So in this diagram, what we've got here is we've got a spring, okay, that is at its free length. So the spring is normally all the way out here. It's this long. This is the relaxed length of the spring. I call it the free length. Okay, you'll see your book call it that also, and some other texts use free length. Now, the spring has been compressed so that it's really small. It's only this big now. It stops here. So this spring has literally been compressed all the way here. So this is the compressed length of the spring. Now, the difference between the free length and the compressed length, if I take this right here, segment, and this segment right here, we know that by subtracting them, we'll end up with this segment right here, which is the distance it's been compressed. This is X right here, the distance compressed. So we could say that X is equal to X free minus X compressed. Okay? So again, you don't have to memorize this formula, just use logic after this from this point on. The free length minus whatever the length of the spring is when it's compressed, this length here, gives us overall X, which is the actual distance that the spring has been compressed. Now, the same thing occurs with stretching the spring. Okay, so when you stretch the spring, we're going to look at the free length minus the stretch length in that case. Example 5 says a spring is compressed from its free length of 2 meters to a length of 0.5 meters. So we have some sort of compression already. if the rigidity of the spring is represented by a stiffness of 50 newtons per meter, so again it would take 50 newtons of force to stretch the spring 1 meter, or compress it 1 meter, then how much potential energy is stored in the spring? So let's write down our givens. The free length is 2 meters, the compressed length is 0.5 meters, so x is simply 1.5 meters. That's the amount that the spring has been compressed, 1.5 meters. The spring rigidity, or the stiffness, is 50 newtons per meter. We are trying to find the potential energy, so we can just simply plug in. This is a pretty simple example. Now what we're going to notice in the next line is to take a look at our dimensions here, and we'll see that we have newtons per meter for our spring constant. That's going to give us a quantity of 25 in the front. But then at the end here we have 1.5 squared, which is 2.25, but that's in meters squared now. So what we can do is we can cancel our meters in the bottom with one of our meters up top, yielding a solution of Newton times meter, which if we recall and go back to our work energy theorem, work is measured in Newton times meters, which is joules. So just proving again that this does turn out to be a unit of joules. And our answer is 56.25 joules. So that is the amount of energy that is stored in the spring when compressed a distance of 1.5 meters with a spring constant of 50 newtons per meter. And your homework for this section is from 4 different pages here, each ranging from kinetic energy to potential energy in springs.